Very good. I like the way you responded to me. Respect. Very good. Okay. Lecture number five. Lecture number five. We're gonna discuss dynamics. So things related to kinematics will be left behind. And from this on, we need to discuss about the forces. So far, no forces whatsoever, but now we need to discuss about the forces. And we have a little bit of challenges ahead of us. Remember, I said last week that the last week lecture was the hardest lecture you could have faced in your master level classes. I wasn't really honest with you because today the subject matter that I'm about to discuss with you is the hardest that you're going to see in your master level studies, the hardest class that you have ever experienced in your life. So, are you guys ready to see the challenge? Good, very good. So, this is going to be challenging because we need to discuss about something that is seemingly simple, but mathematically quite involving. That's a virtual displacement. So we really need to understand why we do the virtual displacement. What is the role of virtual displacement? And then something that is heavily associated to that, and that's a virtual work. You also need to understand the difference between the work, real work, and the virtual work, because those two things are completely different. And you should not mix them ever. So what are those two things? And why we do that, that all should be clear after this lecture. And then there's one more lecture to go because today is already lecture ID 5. One more lecture, and then we are more or less done with the dynamics. And that's when we are simply setting external applied forces to be equal than um, external applied forces to be equal than inertial forces, all expressed using generalized coordinates. And then we just take constraints into account. That's the end of the story. That's going to be our equation of motion. Next week, we are able to run simple mechanisms such that we're solving the dynamics. So that's going to be my target here. And then the lecture number 7, which is just before midterm exam, is all about the summary, all about the recap. We're going to go over the entire topics that we learned in the 6 weeks. And then you have your opportunity to discuss. And if there's anything that is unclear, this will be a good time to let me know that you need extra help here and there. So that's my plan. So that's how it's going to go. But again, like always, we get started from summarizing what we discussed a week ago. So a week ago, we conducted the first analysis. So we did kinematic analysis. And very important to understand that the kinematic analysis can be made for systems that having 0 degrees of freedom, and only for systems having 0 degrees of freedom. The kinematic analysis is all about motion, nothing about the forces. So this is all based on the constraint equations. And we can have different kind of constraint equations, the ones that are limiting the motion possibilities, and the ones that are driven mechanisms to be from one configuration to another configuration. With these constraint equations, or set of constraint equations, we can solve the response. Response is in position, velocity, and acceleration level. And then we increasing the time, and we redo it. So that's how it goes. So that's the procedure behind. Position level, that's the hardest, definitely the most complicated one, because that's going to be based on iterative process. An iterative process is something that we need to repeat it until we reach the solution or the destination that is close enough to our predefined error tolerance. And we can do that by computing something that is called Newton difference. And the Newton difference is this one. This is an information how is we should update our generalized coordinates to reach the destination at any given time. So make sure you understand that that's not a final solution, but the direction where to go to get the final solution. How it's going to go, we're going to take a look at the iterative process momentarily, but position level is typically the most complicated one. The next one, which is velocity level, is the easiest one. Easiest because that's all matter of substitution. And this time we're speaking about somewhat simple substitution because we have here something that is called Jacobian matrix, as it is here too, and it needs to be inverted no matter what level we're speaking about. So it needs to be inverted in a position, velocity, and an acceleration level. All right? And then the another component needed here is your constraint equation differentiated with respect to time. That's all needed. And then acceleration level, substitution too, but this time a little bit more involving substitution because the components needed are a bit messy. So components like the one in here in the middle is a big pain, so it needs a little bit of computing to make it happen. But other than that, it's somewhat straightforward. Now this iterated process, like I mentioned, is this one here. So this is how you reach the position level estimation. So this is an estimation. So it goes in such the way that you derive the constraint equation and you compute the Jacobian matrix. Jacobian matrix is all about the partial differentiation procedure. So you differentiate your constraints, which is a vector, with respect to your generalized coordinates, which too is a vector. Partial vector is going to give you a matrix. This time it's going to call Jacobian matrix. All right? So constraint equations and then using symbolic math tool to compute the Jacobian matrix, those are the ingredients. Those are the kind of what you need in the beginning. Next step, you're going to compute the Newton difference like we discussed last slide, and then you're able to update your coordinates. You will get the new set of coordinates, and you will get it like this. And then you update your Jacobian and constraint, and you're checking whether or not the estimate, whether or not the distance to your final destination is good enough. If it is good enough, you can close it. If not, you need to make another round. And then once you're done with that, you're moving on to velocity level, acceleration level, and then you're increasing the time, and you go again. Okay, that this one. This is this predefined. You're asking this one. Okay, this is this predefined tolerance. So it's something that the user can typically set. So each of the software they're asking, okay, what is an accuracy you want me to do my computing? And this is called tolerance. And there's many different ways how the tolerance can be computed. The way that is explained here is a little bit of overly simplified because now I'm saying that the delta of the vector, and this is not exactly how it goes. Usually it's computed in a way that you're taking out the length of this vector, and if the length this then is then used in this tolerance definition. But again, it's all about the user-defined tolerance. And if it is lower than the predefined tolerance, then you're done. You can close it. So it's like how far off you are from the final destination. And if you say that you're only like 5 meters away from the final destination, then it's okay to make an assumption that it is close enough. And now I'm speaking about the GPS systems you're using in your car. 5 meters in a mechanisms for sure is not enough. Okay, good question. Anything else? I think that I made a mistake. So it looked that I came to a different class. I came to class that is entitled a simulation of mechatronic machine. The one that there was a lot of laughing, a lot of stuff like that. And now somebody died. So what happened? So what happened? It's just this week. Today is not a good day, right? Yeah. It happens. It's like a vibration. The life is like this wave motion. There's up and downs. Today is a little bit down. Yes, sir.
Will we get any tutorial video how we use the MATLAB for solving the velocity acceleration and what you did the last class?
Okay, so that's a good question. So for online participants, the question is that is there going to be some kind of the recorded tutorial how to use a kinematic analysis? There is at least one video that is made by Suraj, Dr. Suraj, that is related to how to conduct the dynamic analysis, then how to solve the equation of motion. We'll ask from Suraj.
I saw the video. I couldn't get everything.
Yeah, of course not.
Newton-Raphson method.
Of course not, because there is a lot of things that you are not aware at this time, but you will be aware of them later. So what he explained to you is something that you will learn in 2 weeks' time.
That's why I could not.
Yeah, that's why it was understandable. It would be a miracle if you would understand it.
So
So yeah, yes, yes, sir.
I is a
It's
number of iterations, right?
yeah, number of iterations. Correct. I is a number of iterations. Correct. Okay, take up your matrix that I mentioned earlier. It's just a parcel operation. So you take one vector and do differentiate that with respect to another vector. That will give you a matrix. A matrix, as you know from your algebra classes, can maybe invertible if it is skew in size. If not skew in size, forget about it. You cannot invert it. So that's where the number of degrees of freedom zero comes from. So you must have equal number of unknowns and equations. Equations this time are constraint equations and unknowns are generalized coordinates. And now when you do this differentiation with respect to equations, which is the C, with respect to unknowns, that must lead to the skewer size matrix. If not, something is wrong. And you cannot invert it, you cannot solve the kinematics. Very good. Very, very good. Okay, then, are you guys warming up? Because now we're going to go to the deep end.
Okay.
So the next that I'm about to explain to you is the hardest that you have ever seen in your master level studies. And take it easy. We're going to go slowly. And if something is unclear, raise your hand and then we can discuss that. Okay, so we're going to use something that is virtual displacement, virtual work to create something that is called generalized external applied forces. So, big picture is this. So, according to Newton's second law, dynamics can be solved by using this equation. This is external applied forces. This is inertial forces. Now, what we're going to do next is that we're going to take each of these force components and we're going to express them by using the unknowns that we set when we define the kinematics. Unknowns are called generalized coordinates. And one body in planar case needs three generalized coordinates. So now we just need to make sure that the forces are expressed by using these set of unknowns. That's going to be our target. And to make that happen, we can use this concept called virtual displacement and virtual work. Virtual displacement is, I think, it is a more important virtual work, of course, too. This is how we're going to get the equilibrium when we are setting these two forces to be equal with respect to each other. Okay, so the challenge, oh, this is what I wanted to explain about the level of difficulty. So each of these is, these classes, 1, 2, 3, 4, 5. So we're here. And I say it was like this, but today we're going here. And I claim that this is the summit of the mountain. It wasn't. Now the next topic, which is this generalized external forces, is the summit of the mountain. So we need to climb a little bit, and the rest is downhill. So you're ready to hold my hand, and you're ready to go. You're ready to go. Very good. Okay, again, let me emphasize the target, what we wanted to do here. So we wanted to express the force, a force component, which here is expressed by using global coordinates. You see that the force vector here consists of two components. And these two components are with respect to our global coordinate system, x and y. That's why there is a two components. The one that is related to global x direction, another one that is related to global y direction. This force is not good for us. It's not good for us because I would like to express the same force but using the unknowns that I would like to deal with. And the unknowns that I would like to deal with is, of course, my generalized coordinates. And where is that they coming from? They coming from my kinematics. The way that I'm setting each of the points, each of the particles, which do not have the rotational degrees of freedom. The particles do not have the rotational degrees of freedom, and I'm expressing them by using this equation. Okay, how can I make this happen? Okay, I think that I can make this happen by using the mapping. And the mapping I'm able to conduct by using a concept of virtual displacement, virtual work, to be more specific. So that's going to be my target, to get from 2 components to be 3 components. So that's what's going to happen. All right. And then I know that this point where the force is applying can be defined by this kinematic equation. So it's not too complicated. So it's somewhat straightforward. Please understand this too, that this vector here is expressed by using global coordinates. So it is expressing the point here with respect to x and y axis. But the unknowns that are hidden to this equation, there is a total of 3 unknowns. You're still with me? Very good. Okay, virtual displacement. So virtual displacement, there's a little bit of writing here. So my advice you to think about the virtual displacement is not to think about it. And so what that means. So displacement is the first word you need to take a look. So you can think about the displacement, but don't get confused about virtual. The virtual is something that defines how we're gonna introduce this displacement. There's a specific idea behind the virtual displacement. But if we think about the displacement, that is that there is a r vector r in a 1 point, and then the vector r, let's say that in a one time moment, and when the time is equal to something like 0, and when the time is equal to something else. That difference here, this one here, is called delta r. Big thing about this, that this is a real displacement. The real displacement takes place in such the way that the time is running. So if I'm moving my pen here to here, I'm not able to move it without time running. So when I'm moving something, the time is running. Virtual displacement is a mathematical thing. So it's a mathematical thing where we are assuming that the time is not running. Where you can see that in a real life? Nowhere, because that's not just possible. Not possible to do the displacement such that the time is not running. At least I haven't seen that to happen. Have you? No, that's not possible. I mean, we don't speak about the quantum mechanics, but we speak about the bigger mechanics. So it's not possible to introduce the displacement without time running. Virtual displacement, we are assuming that the time is frozen, which of course is not possible. But that's going to give you something that is mathematically very, very valuable for us. It's going to create mapping between the different coordinate systems, and that's exactly what I'm after here. Because remember, we actually are mapping 2 different coordinate systems. The one that is global coordinates, another one that is generalized coordinates. So I'm looking for it. What I'm actually after is the mapping between 2 different coordinate systems. One consists of 2 components, another one consists of 3 components. All right, so that's what I'm after here. Okay, so as mentioned here, the virtual displacement, we're considering the time is not running. Sometimes people get confused, like, okay, displacement, virtual displacement, it says that it's very small. How small it is? Forget about it. Not important. Think about just math, and think about what is the ultimate call here, finding a relation between 2 different coordinate systems. A virtual displacement will do that for you. Virtual work is like, well, let's get started from the work. The work is a force multiplied by displacement in the direction of force. That's what the real work is. Virtual work is same, but displacement is going to be virtual displacement. So that's what it is. So those are the difference. So let's take a look. Let's take a look at this system. Let's take a look at this beam-like body where there is a point force applying in a point particle, which is O particle here. I know that the O particle can be expressed its location with respect to global coordinate system can be expressed by using the equation that I'm very much familiar with. All right. And this vector here, this force vector, obviously is having expression in a global coordinate system. So it consists of two components, which is Fx and Fy. So those are the two components. All right. So now this is a kind of the situation mentioned in another way around. So we have here a position and another position, and then we have a force. So what we can do for that? I'm going to skip this. Not going to explain this in a thorough way, but let's first look about the work in the real work. So we have a displacement where the r is moved from this position to this position, and this one here is obviously delta r, which is a displacement in the direction of force. All right. But when you look at the math here, when you compute this delta r, of course, it's going to be computed in a way that is partial r, partial t. T, of course, here is a time multiplied by delta t, because time is running when the displacement takes place. And then this is multiplied by partial r, partial q, delta q. Virtual displacement, same, but like was mentioned a little while ago, time is not running, meaning that this guy will be set to be equal to 0. So what that means? It means that then this delta can be expressed in a little bit simplified way. And now what I'm going to do to make sure that you understand the difference between the real displacement and the virtual displacement is that in a real displacement, I'm calling that as a delta here, like this. In a virtual displacement, I'm calling as a delta. But this, my notation is different. So you see that they're not the same. All right. So when you do this, so when you look at this virtual displacement, so you can only take this last component into account. And when you look at how this last component reads, it says something that is very important for us because it says partial r, partial q. R, remember, is expressed by using global coordinates, two components. Q, three components. So this will actually lead to a matrix where there will be 2 rows, 3 columns because of, remember, this partial operation. Then that is then multiplied by delta Q. So we're switching the virtual displacement to be expressed by using generalized coordinates. And when we do that, there's something that is very useful for us during this process, or is created during this process. And this is the mapping matrix that appears to be here. Okay, now this started to make sense, right? Because what we're going to do then, when we look at the force, the virtual work, is that we have virtual displacement, this guy here, multiplied by force expressed by using global coordinates. Okay, what we need to do here is that you guys need to breathe really deeply. Okay, and let me repeat it one more time because I know this hurts. This physically hurts. Correct? No pain. You don't feel the pain. It's like this. So you don't even know if it is a pain or what it is, but definitely it hurts. Okay. Again, what we wanted to do here is that we wanted to find the relation between two different coordinate systems. We're going to introduce this relation by using something that is called virtual displacement. And when we're using the concept of virtual displacement in virtual work, this is where we're going to get the mapping. And this is how we'll be able to express the force initially expressed by using global coordinates, but future expressed by using generalized coordinates. All right. You see that already happening because it's here, this delta R. It is already expressed. The force is expressed by using global coordinates, as is displacement. as is displacement. So we're going to switch the displacement to be expressed by using generalized coordinates, by using this relation. Can you see my handwriting? So this is delta R and delta Q. Q consists of three components. This consists of two components. This is two components. This is three components. This is a matrix where there's a two rows, three columns. Here's a relation. This is what we are after here. So that's what we wanted to find. And when we multiplying forces by this matrix, it's going to automatically create us three force components associated to generalized coordinates. Beautiful. Yes, sir.
When we used to firstly differentiate, partially differentiate with respect to position, we used to get the delta q, and that was because of the fact that q also was dependent on the time. So
So this one, this
yeah,
is the real work. This real work.
real work. And
Real.
yeah, we
Yes.
used to get that because position was also a function of time as well, because
Yes.
depending on
Correct.
time.
Correct. Correct. Exactly. Exactly.
But now, since it's we are not considering time, so we are considering only position. So when we partially differentiate the equation again, I don't think that delta q should come there, because it's going to automatically differentiate itself, because we are only differentiating with respect to the position.
Okay. Okay. So you're saying that this guy should be eliminated.
Ah, yes, because we're going to completely partially differentiate it
All
with
right. All
respect to
right.
position.
Okay. This is a very good thing. So this is a it's a fantastic question. So you're saying that is this delta Q actually needed?
Yeah.
Okay. This story is I guess it is against university laws to come and hack you, but and I will not do it. So you can be safe. You're safe.
Yeah.
But this is a fantastic question, which I was hoping to release this topic to you next week. It is related to how you're gonna set the equation of motion. But it is true when you have used and studied about the virtual displacement. Typical scenario is that you say that this one here, this guy, is disappearing. It is disappearing because it's sometimes they say that because it's small, because of this and that. It can disappear. It can disappear. It is correct that it might disappear, but under the certain condition only. And the condition that it disappears is that the displacement, this displacement, which is introduced here, need to be kinematically admissible. I'm going a little bit ahead of the time, but there is a condition when it disappears. If you don't do this displacement such the way that is kinematically possible displacement, it's not going to disappear. But we need to get back to that. But it's a fantastic question. Are you sneaking out my lectures from last year, or how you knew this? Just something like this.
No, I'm used to that. Yeah.
Fantastic, fantastic question. All right, so I was here. I was here. You know, this delta r can be expressed in such a way that it relates our global and generalized coordinates. And this is the one that's doing the relation. All right. Now, if we look at the details, so if I do the partial differentiation, which I'm not showing in details to you. So you can take a look at the lecture notes if you wanted to learn the details. But if you do the partial differentiation, it's going to give you the matrix, like I said, consists of two rows, three columns. And these columns are associated Rx, Ry, and angle theta. These ones are associated to X and Y coordinates of our global coordinate system. All right, now they started to make sense because, okay, there's a little bit of notation. So you notice that, this can be simplified in a way that this something we learned in a case of velocity can be make it handy here and it simplifies the notation. But when you use that in a forces, then the forces can be expressed as it is shown here. Now, let me explain again. Here's the whole story. So we started to express the virtual work. And in the virtual work, I have here delta R expressed in a way that the time is not running. And because the time is not running, I can use this relation. Sorry about the transpose operation. So they're a little bit confusing, I admit that. but they should be correct. Everything should be very much correct now. So you can relate delta R and delta Q. And why you related that, or how you related, is this partial operation. And now this partial operation can be simplified and can be written like this. That's the whole story. Again, so we started from the virtual work. In the virtual work, we have delta R, and delta R can be used, can be expressed in a way that it relates R and Q. R consists of two components, Q consists of three components. Makes sense. All right. And then when we do it, and when this mapping matrix is used to multiply that by forces, we're going to get three force components associated to correct generalized coordinates. So the mapping is done. So we complete the mapping. How you like about this? What this matrix is doing for you? This one. Let me repeat it because it's going to be my in-class quiz. Yes, it's my in-class quiz. It relates global coordinates and generalized coordinates. It is not describing the rotation of the particle. It is not describing color of the body, dimension of the body, anything like that. All that is nonsense. Nonsense. So it's describing relation between two coordinate systems, and these two coordinate systems are global and generalized coordinates. Makes sense? Okay. All right. So finally, my forces are expressed like this. Actually, there is a clear interpretation of what these forces are, because you see that this vector, force vector that is here, originally expressed in global coordinate system, is affecting my Rx and Ry. That makes sense, because those are the ones that are describing the translation in a global X and Y direction. Only additional component is a moment. At the moment, it is describing, if I have here global coordinate system X and Y, and I have potato-shaped body, and the force is applying here, it is expressing like if the body reference coordinate system is here. You see that what this is doing, it is a moment to the level due to the level arm. That's what it is. How much that is introducing rotation, because the third generalized coordinate, or the third component in my vector of generalized coordinate, is angle theta. So that is must be related to how much rotation that is experiencing, and that needs to come from the moment. Okay, what's going to be the third component if the force is imposed to the origin of the body reference coordinate system? Zero, because this guy will be zero, so it will be no moment. Makes sense? How many force components is in a vector of generalized coordinates per body? Three, because three unknowns, three components. Second component. Okay, so this is a bit messy. So this vector consists of three components. Okay, first component is x along the x coordinate axis. Second one along the y coordinate axis. And third one is this whole set. So it's a single component expressing how much moment the body reference coordinate system is experiencing. It's a little bit confusing notations. Oh my God, so what a big surprise. So first in class quiz is a physical interpretation of matrix, partial R, partial Q. In case of virtual work, defines relationship between the global coordinates and constraints. Constraints. Defines relationship between the constraints and generalized coordinates. Defines the relationship between the global and generalized coordinates. Oh, I see, by the way, this is different than in my Socrative, isn't it? Have you guys looked into my Socrative yet? Let me double check that. Nothing on it. Nothing on it. Okay, let me take a look. Oh, you don't see this. Uh, it should be on. Okay, so what I have here, okay, so this is a bit confusing. So my Socrative, I did not update it. I did not match this with my slides. I want you guys to use this one. Invite students. Okay, sorry. What? No, I don't want to use this. Live. I think that I made some kind of a mistake. Finish activity when I was launching this. So let me launch this again. So I want to go launch, squeeze, this one, teacher, launch. Can you see it now? No. Oh, okay, okay. Sorry, sorry. Guys, I'm in the wrong class. I'm wrong room here. So I need to switch this one. Okay, I was in no, 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 not this one either. So I need to launch it. Launch, finish activity. You see it already. It's coming again. Will come again. Okay, can you? Okay, now guys, take a look at what is in a slide here. So this is not matching with my PowerPoint. So I'm saying here, defines the rotational particle, like always, always. Okay, so it's good. Okay, so the options are defines the rotational particle. Remember what we are created about particle and its rotation, and then defines the body dimension, defines relationship between the global and generalized coordinates. The final option is defines relationship between the external applied forces and constraints. And the success rate is how much? 80. I'm sensing a big surprise here. I'm feeling. Can you feel the vibe? I feel the vibe. I feel the 100%. You don't feel the same. No, no. Impossible. No, it's not impossible. Okay, so let me see how many answers we have. So it's a 54 answers. So we're gonna wait a little while, and then we will continue, and we're gonna practice. I have two examples how to use external applied generalized forces, and then we're gonna discuss how we're gonna handle that in the case of inertial forces. That's gonna be, and then the mission is accomplished, more or less, almost. Okay, question in online participant. Are you going to what? Tell us the same thing next week? That this is a no. You need to trust me. This was the hardest. This was the hardest. So rest is the downhill. So we reached the summit. So how it feels to be in a summit? Can you enjoy the view? Yeah. Yeah. So is it feeling good? Yeah. Well, yeah. But you need to trust me. Hey. Okay. So I got 61 answers, and last week it was 80, 80, 70, 80, something like that. So maybe it's going to be more. But I see the class today is a little smaller than a week ago. Online participant. How many online participants? How many online participants there's today? 50. So it seems that many are decide they don't want to come here. Understandable. That is understandable. Okay, so let me take a look. So it's 61 answers. We're gonna wait a little while, and then yeah, then I will revisit in that in class quiz. Now I need to unhook this one, put this in a presentation mode, and put this back. Okay, here's the first example. I have here again beam-like body, and there's a one force only applying this beam-like body, and that's a gravity force. Gravity force is applying in the center of the mass, and the center of the mass for a or in a beam-like body is obviously here in the middle. So this is my force vector. And the force vector, or the component of the force vector is such that the x component is 0, obviously because the gravity only is applying, and the second one is a mass multiplied by gravity constant. Okay, minus direction, of course. So that's my forces. Again, two components. And what I would like to do with these forces, I would like to express these forces by using three variables that are my generalized coordinates. And again, my generalized coordinates are Rx, Ry, and angle theta. You see where the body reference coordinate system is located at. So it's located here in one end of the beam-like body. So obviously, I'm going to have three components, non-zero components. No, let me correct that, because the first component is zero component, but the third component will be non-zero because force is not in the center of the body reference coordinate system. It would be a different situation if I would move my body reference, if I would move my body reference coordinate system to be here in the center. Then that would mean that my third component will be equal to 0, but not this time. So let's see how it goes. So I'm going to use this matrix that I defined a couple of slides back. And again, there is a transpose operation. So this is an identity matrix. And then the one that is defined the moment, level arm would be the better way to say this. And then this is my force component that consists of, two components. And when I'm using the information about where the U bar, where the point where the force is applying, with respect to my body coordinate system, then I have all the necessary information. So the vector U bar is L divided by 2 because look where the body reference coordinate system is located. And this length here is L divided by 2. And this direction, this extra y direction, I need to move 0 coordinates. Okay? So when I'm using this information, my force component reads like this. Again, these two components are copy-paste from my original force vector. Third one is the one that is introduced in the moment arm. You see that is a function of the body orientation, which makes sense. Because if the body is pointing like this way, then again, it will be in the same direction that the body reference coordinate system, and the level arm will go to 0. Okay, makes sense. Next in-class quiz. Let me explain this to you. So have the same body, same beam-like body. Everything exactly like I explained, with the major difference. And the major difference is the fact that now the body reference coordinate system is moved in the where the body reference, let me explain this another way, where the center of the mass is located. That's where the force is applying as well. So how is going to be the vector of generalized forces? First, you need to figure out how many components you need. That's going to be the first thing. Because some of the options you can see here is offering incorrect number of generalized coordinates. So those obviously are incorrect. The next thing you can do is that, okay, how much is a third component? How much is a level arm between the body reference coordinate system and the force? That's the way to solve that problem. Okay, but prior you to that, so let me take a look at this one. And the cases were 90%. Was it 90% success rate? This in-class quiz? Okay, good news. I have a very good news. Super good news. Good news is this. So we still have 82 participants because the number of participants reflects the number of people that will pass this course. Those are heavily related. I can even make a scientific study about that, but that's how it goes. Okay, but what's the success rate? 98, 98, 70, 70. That hurts my heart. You say 70, because it's going to be high, much higher than that. I'm saying more than 90, more than a 95, more than a 95. 90. Okay, not 95, but 90. That is a fantastic news. You cannot see it. Okay, and you don't trust me. You don't trust me anymore. I see that. Okay, so what about this? Okay, okay, very good news. Very, very good news. 90% success rate. Minor drawback is that still there is something thinking that maybe still there is a minor chance that the rotation of the particle is still existing. Incorrect. No, it's always incorrect. Always incorrect. Always. Always. Okay. And then creates the defines the body dimension incorrect. It defines the relation between the external applied forces and constraints. We did not discuss about the constraint here. It's not related to this subject matter. The constraint will come back at the time we're looking at how we can set the equation of motion to be the way it's going to be. So it will come back, but not right now. Okay. And the next in class quiz, let's put it on. So it's going to be, so you need to take a look at the slides. And here are the slides. Okay, so you see that. Let me see if the online participant, they can see it as well. Okay, so yeah, I'm not going to read it, but as I advise you, take a look at the number of force components. Those need to match with the number of unknowns, which have to match with the number of generalized coordinates. Okay? And then the last thing to solve is that, okay, what is a level arm? If the level arm is 0, then the third component needs to be 0 as well. And success rate is what? 110%. 82. So yeah, I think I see that you're thinking that this is going to score better than the last one. Okay. Should I take a look? Or should I leave this and get back to this a little bit later? Okay, let me take a look because there's a bit of the delay for online participants. No, I shouldn't take a look at that, but this one. Okay, 50, 60 answers already. Maybe this is a jackpot. Maybe this is 100%. It could be because then I think that we have all the elements, all the ingredients, all the components to score 100%. I think we have 68, 68, 69, 70 is always increasing rapidly. So the last ones, speed up, and then we're going to take a look at this. How you see what is the number of online participants? Because there's like, at this time it seems that it's a 50, 50. Yeah, it looks, it's changing all the time. Okay, 74. So last ones, speed up. You guys all done? Good. The last online participants, I'm gonna close this momentarily because I want to see how it is. Okay, the 76. Last time it was 80, 82 if I remember correctly. So we're not far from that. So the last ones, we're gonna close the case. And the correct answer, okay, the last minute answers are coming. So the correct answer is, of course, the first option. First one. Disappointingly low. This is the lowest ever, isn't it? It's never been this low. Okay, so what went wrong? Okay, so we're going back to this slide. So we're getting, again, we have two guys, forces and generalized coordinates. No, I'm not going to do that. I'm not going to get started from the beginning. I was just making you scared because I was thinking that if not carrot, then the stick. Okay, so we're here. And let me put this back in presentation mode. We're going to take, I know that it's already time to have a break. So would it be okay if we do this one more example, then break, and then the last thing? Okay, the last thing that we need, a second last we need, before we're able to create the equation of motion, will be, I'm going to explain this to you already. Because remember, this is where we started. This is external applied forces, and we already know how to express this by using generalized coordinates. You know this guy, D'Alembert? I'm sure you heard about it. He was a world famous. And he became to be world famous because he was playing with this equation, and he was able to write this equation in this way. And this is it. What a miracle. He was really smart. Really, really smart. And he became to be so famous that everyone knows his name, D'Alembert. There's a lot of awards and everything, D'Alembert's award, even in my community because of this. No, there's a bigger story than that. But it's seemingly like, come on. No, that's not so great accomplishment. But there's a bigger story than that. The bigger story is that he realized that the inertia forces can be treated the same way than external applied forces. Inertia forces can be treated same way than external applied forces. So what that means for us, it means that we can redo the whole thing, but for inertia forces. Correct. Correct. Exactly. But before that, here's a next example. So I have here a body which is a triangular in a shape, and body reference coordinate system is located here in one corner of the triangular shaped body. And then the two forces, both expressed by using global coordinate systems, are applying in another corners of the triangular shaped body. So here's a point P, force applying is a 10, 10, and then the point A is the same components, and my vector U bars for both of the bodies are expressed here. So I'm gonna express these two forces by using generalized external applied forces. So again, I'm going to take a look at where the force is imposed or applying. Applying is a better way to say it. I'm going to differentiate that with respect to my unknowns. We'll get the mapping matrix, and then I'm going to use the mapping matrix to convert the forces to be expressed by using generalized coordinates. Okay, so that's how it goes. First point, A, which is located here in the lower, this corner here. So I know the vector u bar. So using the vector u bar information, I can express my point A using global coordinates like this. Two components. So it makes sense. Next, I'm going to differentiate that with respect to my unknowns, which are Rx, Ry, and angle theta. And when I do that, that's going to give me this matrix. Two rows, three columns. And when I multiply forces with this matrix, it's going to give me the vector of three components. So 10, 10 are located here, and then the force which is imposing the moment is expressed as a last component. And then I redo the same, but for point B. Here's my point P. I'm going to take a vector u bar into account, so it's going to give me the position in a global coordinate system. We'll differentiate that with respect to my unknowns, multiply my forces, and again I will get the vector of three components, which is a Rx, Ry, and angle theta corresponding those three components. And then I'm just combining them together, and that's going to be my forces in total. That's how it works. Okay, before you are heading to, I don't know if I should say this or not. I'm gonna still say it. I'm gonna make a high risk game. Okay, this is a moments. Moments you can apply. You can move it however you want. So this is a easy game. So I think we don't need to discuss about that. But next challenge. Like I said, we're gonna do the same, but for inertia forces. And I wasn't honest when I said that we reached the summit. I just realized that this wasn't the real summit, this was just the halfway done. So there's a bigger mountain ahead of us. And this one is this is a really big one. Really, really big one. So again, we were here, we went here, or now we're gonna go so high up that my screen, even this room, may not be tall enough to show how you up in level of difficulty will go down. But then, trust me, then this is it. Rest is downhill. Seriously, rest is like very, very nice downhill. It's kind of, yeah, and even goes the minus direction. Minus. I don't know what that means, but it's going to be so pleasant. So the last effort. So here's what I recommend. You go out there, spend there, can it be 5 minutes only? 10, you need 10, yeah, okay, 10 minutes would be good because the summit that is ahead of us is a monster size. And then minutes, and then you will be back, and we're going to take a look at the last effort, last one. And trust me. I know that I shouldn't say, but now you need to trust me because this is serious. That the last effort. And then everything after that is so pleasant that it's gonna be all laughing, laughing after laughing. Yeah. Okay. 10 minutes. He's asking questions or?
asking questions, and I couldn't see the comments that you can. Yeah,
Yeah, now
I
it's
get
me.
it.
So the echo comes from your computer, so you need to put the voice down.
Okay. Let me say.
I noticed that there's one question. Can you see the chat? There's another question in the chat in YouTube.
Chat. I'm
Yeah,
checking it.
this is related to transpose operation.
The chat.
And you need to, I don't know, mute yourself or put the loudspeaker off.
Just muted it.
So it was
Uh,
catching my
yeah.
mic.
Uh, so there is this one question. I would like to ask, why are certain matrices transported?
Yes, that I haven't addressed yet.
Okay.
So the question that why certain matrices are, why is that I'm playing with the transpose operation?
Yeah.
Yeah. And this is just that I don't know which one would be more clear. I think that my representation may not be the clearest because I could use a dot product as well, and I don't use it. I could express this. Are we? By the way, guys, are we? I think we're back here, so we're ready to continue. Okay, there's a one online participant is asking about the transpose operations. And you know that there are two different ways to express the, like for example, this equation. The work is a scalar quantity. So that's clear. And now we have two vectors. The one, like force, is a vector like this. And there's supposed to be another vector which is a position, this guy here, which too is a vector like this. Because both are expressed using global coordinate axis. So they are associated to x and y. So it cannot multiply the two vectors if they are having the same dimension and same form like this. So one needs to be transposed.
Yeah.
Otherwise, I cannot do the operation. I think the mathematically more elegant way to do that would be to say like this: parcel r dot product of force. But because I don't know, because I'm old-fashioned guy, so I don't want to use the dot product, but I would like to use, instead, I would like to transpose one of them. What I would like to transpose is, of course, the first one, because otherwise it's not going to be matching. So I'm going to transposing this one. That's going to give me the scalar quantity, because the work is a scalar quantity. All right. And I know that is a little bit confusing that, these transposes are here and there and they make life a bit more complicated. And I need to think about it a more clear way to express myself. Maybe I should use something else, dot product or something. But right now it's a bit messy. I have to admit that. I need to admit. And now because I'm using transpose here, I'm using transpose here as well. And now this all becomes to be a little bit inconvenient. I admit that. So hopefully, online participant, I'm not going to mention the name, but the one that just asked this question is happy about my response. So it's all about making sure that the dimensions are matching, and all gets started from expressing the work as a scalar quantity. So it's a scalar. Work cannot be matrix or vector or anything like that. It's a one single value. Okay, good. All right, so this is what we covered.
Can we go to the Socrative quiz two?
Quiz two.
Yeah.
Okay, we can go to Socrative squeeze number two. Okay, that disappeared. So the number two was, what was it?
Um,
Force. This one. This is two.
yeah. So I couldn't really. Could you elaborate on that?
Okay, so all right, so it wasn't clear like how this one is the correct answer.
Yeah.
Okay, like I said, the first thing to do is to check like how many components you have, because you have to have equal number of components than number of unknowns, and the number of unknowns is equal to the number of generalized coordinates.
Okay.
So that number must be three,
Yeah.
because I have one body only. So it means that this option is no good,
at all.
this option is no good. So it leaves you to, because you see that this consists of one, two components.
I was watching it online. Actually, I wanted to go for A, but yeah, that's how I lost the points.
Okay,
I fell out in the
but
elevator.
but that's okay because you make another mistake too. And another mistake you did was that, okay, the third component is all about the third component now. And when the force is applying in the center of the body reference coordinate system, it means that the vector u bar is going to be zero. So the level arm, so the moment imposed to the body reference coordinate system will be zero. So it means that this is the only one correct because of the zero. This is incorrect because this implies that there is a level arm, which is not the case. All right? You
Yeah,
agree with me?
yeah, yeah.
Okay, good. Okay, and then we're gonna go. Okay, so now it's like I promised, there's gonna be serious pain that we're gonna experience next. So what I'm, so let me give you an advice here. Okay, hopefully we have a time to do one more in-class quiz. Okay, very good. Okay, here's my advice to you. Don't think.
Okay.
Can you follow that? Okay, this is think about this as a pure math. And as soon as you start to think about this, like, okay, what is a physical interpretation of this and that, you cannot develop the major headache and not understanding much. Later, I will do the physical interpretation for you. But now, you can just enjoy the math. Do you think that you can do that? So it's going to be just pure math. So we're going to do the exactly same thing we did for externally applied forces, but for inertial forces. And we want it to be very elegant because we sophisticated and everything. We want to show off that we're very good in physics and all stuff like that. That's why inertial forces are not expressed the way I said. I said earlier that inertial forces is a mass multiplied by acceleration. Yes, but remember we in a real, world of particles, so we actually wanted to do volume integral. Volume integral over the density of each of the particles. So this is the more elegant way to say mass. So mass can be expressed volume integral over the boundaries of the body such that you're taking density of each of the particles into account. This will be the very delicate, sophisticated way to say the same. But you know what I mean here is a mass. It's a mass. But later we could use this volume integrals too on, planar integrals to figure out the certain inertia parameters. But you're still with me. So it's a mass multiplied by acceleration. And this time, because I want to show off that, I know that the mass is consisting of density. I want,
Density and volume.
yeah, both density and volume. I want to say it like this. This is equal.
Okay.
Okay, so this is just to show off because we're showing off. Yeah. Okay. What next? Next, we're gonna do exactly same because this is what the Dylan Barrett figured out. So he figured out that inertial forces can be treated similarly than external applied forces. So what we can do is that we can compute the virtual work made by inertial forces. So that would be force, inertial force multiplied by displacement, virtual displacement, not the real one, but the virtual displacement. So this is going to be my virtual displacement. This is going to be my mass multiplied by acceleration. This guy here, which I can substitute as here. When I do so, this is how it looks. This is still a virtual displacement. And the virtual displacement, very important you to understand, is expressed by using global coordinates because delta r, because of this guy. This guy consists of two components. I'm not happy. I'm not happy about that. I want to use this relation that I learned earlier today. to express virtual displacement using generalized coordinates, because then my inertial forces are expressed by using generalized coordinates. And they need to be expressed by using generalized coordinates because my external forces are already in those coordinates. I need to make them match. Are you guys doing like, no, it's,
Actually, to be frankly honest, I can't read your handwriting.
okay, so the problem is that you cannot read my handwriting.
Yeah.
Okay, so that's the minor problem. I can guarantee you that. So if that's the only problem, so you're doing really good if this is the only problem you have. Okay, let me try to read this in a more clear way. So I want to say delta R is equal then partial R partial Q multiplied by delta Q.
Okay.
Clear, clear.
Yeah.
Okay, better. Sorry that when I'm standing and this screen is
Yeah.
wobbling a little bit, it's not so clear. Okay, here's the relation what I wanted to use. Why? Because I wanted to express my virtual displacement by using my unknowns. This guy, generalized coordinates. Okay, that's what I'm after here. And again, what's going to be here is my mapping matrix. That's what I'm going to use. And now when I use this relation, I can express my virtual work in such a way that it is delta Q. Delta Q. Very important for me. And then I have here this mapping. And then still I have the bit of the problem because my acceleration is still expressed by using global coordinates. Not good. So I need to do something for this guy too. So I need to be able to express my acceleration such the way that I'm taking my generalized coordinates somehow out of it. But anyways, this is going to be the way that I'm going to express my virtual work. Excuse me, not my virtual work, but my generalized inertia forces. Generalized inertia forces is a inertia force is expressed by using generalized coordinates. Okay, generalized coordinates. So I have here my mass multiplied by acceleration, and then my mapping. Nothing but mass multiplied by acceleration multiplied by my mapping. Okay, here comes the next big pain. Next big pain is this, that I wanted to reformulate my acceleration. I wanted to reformulate in a way that my generalized coordinates are more explicitly mentioned, because my original expression of acceleration is this one here. And now my generalized accelerations are hidden there. So that's not very convenient. So I wanted to express this in a way that I have here a vector that consists of acceleration of generalized coordinates. This is then multiplied by this mapping matrix. This is coming directly from the math. Nothing but another way to express this equation. And then another component which is quadratically related to velocities. So that's going to be my acceleration. This already is a very bad news for us. Because now if the acceleration consists of two components, one that is linearly related to acceleration and quadratically related to velocities, my inertial forces will consist of two components. One that is linearly related to acceleration, which is going to give me a mass matrix, and something that is quadratically related to velocities, which is going to be giving me quadratic velocity vector. So it's going to give me two components instead of one. But that's because the way I'm expressing my kinematics. Everything is a consequence of the way I selected my kinematics in the very beginning. Okay. Now, here comes the biggest pain you have ever seen in your life. Because here's my acceleration, the one that I got from the previous slide. Here's my mapping, which is a partial R, partial Q. When I do substitute this material to my generalized inertial forces, the one that I got from previous slide, it becomes to be this big hassle here. So this is going to be the monster pain, big pain, the biggest pain ever so far. But that's okay, because it's just a math. Let math do it for us. Let's not think about any further. Let's just do the operation. Let's take a look how it appears to be. So let's just continue here. Another step and we are almost there. Another step, it's going to be like this. So when I do matrix operations, so when I do all these mathematical operations, I started to see, okay, there's going to be a component that appears to be linearly related to acceleration. Now that's going to be something called mass matrix. Mass matrix that will consist of the mass of the body and mass moment of inertia. We'll take a look at that in a momentarily, like how it looks. And then there's going to be another component that is called quadratic velocity vector. Because remember, there's a last component that is quadratically related to velocities. That's going to be my last component here. Here's what I'm proposing here. Let's forget about the last component this time, because last component may be equal to zero. In certain conditions, it could be said to be equal to zero. So maybe we can forget about it. That's for a little while, and revisit that next week. But still, it's going to be not as bad as that you can see in this slide. So this one is really at the summit. This is it. The next, we enjoy the view. This math. Take a picture, selfie of this math, and then we started to go down. How that sounds? Any doubts?
Very much.
Very much doubts.
Yeah.
Okay, relax. There's a lot of things that it's just a pure math. And if you want to exercise, if you wanted to do these things, we could practice the math a bit later. Okay, but let's take a look at something that is more important for us. This component that is linearly related to accelerations. Let me go back this slide here. So I'm speaking about this component. When you do this math, yes, yes. R dot dot. This guy, this consists of two components. So it's a vector because it's written in a bold font. And this guy here, this vector in total consists of three components. So two of them are, Rx, Ry, angle theta. Okay. Another. Okay, so this here, this is identity matrix, 2 by 2 identity matrix. This is a scalar quantity. This is a 2 by 2 identity matrix. This is a scalar quantity. So these are the vector, 2 rows, 3 columns. So they're going to give me the matrix of 3 by 3 in dimension. That matrix is called mass matrix. This is what I'm about to show you. This is called mass matrix that is associated to my generalized coordinates. So each of the body consists of 3 by 3 mass matrix. And mass is associated to Rx, Ry, and angle theta. Or more specifically, more correctly to say, acceleration of Rx, acceleration of Ry, and angular acceleration. Okay, how that look like? This look like a 3 by 3 matrix that consists of 2 by 2 submatrix here that is associated to Rx dot dot, Ry dot dot. When you take a close look about that, that's going to be identity matrix, density over the volume integral over the density of the body. What is that? Mass. Mass of the body. So it's a 2 by 2 identity matrix where the diagonal components are mass of the body. Mass of the body. Makes sense because if you have a Translational acceleration, the only one that resists that is mass. Nothing but the mass. It doesn't matter if you go this direction or this direction, it's going to resist your motion the similar way. Makes sense. So it must be correct. Then there is a one that is associated to rotation, theta. And if you take a close look about that, that's exactly same than mass moment of inertia. So if you look at the mass moment of inertia from your, I don't know where you're going to look at that, but from your notes from high school or junior high school, high school, high school. When you, I think you learned this in a high school. This is exactly the same that you can see in a high school notes. So it's how much rotation is resisted because of the inertia. That's what it is. You know that if I'm rotating bend here in the one end, it's going to be different than I'm rotating here in the middle. That's what it is. You can try this. This you can try home.
Yeah.
Okay? All right, so you see, you know what it is. So it's mass moment of inertia. And then something that is combining the translation and rotation that may be equal to zero. Under a certain condition, this could be set to be zero. You can kind of see this condition already. You can see that if there is a, if the mass of the center of the mass and the body reference coordinate system happens to be in the same place, then this is going to be equal to zero. So that simplifies mass matrix. Okay, mass. If you think about the mass will never change depending where is a reference coordinate system or body reference coordinate system. If somebody claims that my weight is different comparing where's my coordinate system, that's not true. That of course is nonsense. Mass moment of inertia depends where the body reference coordinate system is located at. Okay, so don't get confused about that. All right, so here's an example. So let's do these two examples, and then my last in-class quiz, and then you're off the hook. But you know, when you do the mountain climbing, which I don't do, but I have watched movies, so I know quite a bit about that. So it's very dangerous to go up to the summit of the mountains, but it's equally dangerous to go down. And now we're going down.
Okay.
I heard that it's more dangerous to come down than it's going off. I watched the movie. Mount like Everest or something.
Yeah, yeah.
They all died in a way down.
Yeah, yeah,
So
yeah.
it can happen. So we
Yeah,
need to be super careful here.
yeah.
Okay. All right. So here it is. So I have a box-like body. Box-like body. Body reference coordinate system is located in the middle here. And I wanted to figure out my mass matrix. And the first thing to compute is this 2 by 2 matrix where these diagonal components are mass of the body. So I can do this this is really showing off way that I can do the integrals first in this third dimension, which is provided as a W. And then I can do the integration from x direction from minus L divided by 2 to L divided by 2. And then this other direction from minus h divided by 2 to h divided by 2. You don't need to do this in this complicated way. So it's enough to just to say the mass, put it in a diagonal component of 2 by 2 matrix, and that's it. That's going to be my first component. Second one, I can again show off about my math skills, and which is almost non-existing. And you can do this integral, and you know that this integral will provide, because a single component here, that's going to give you 0. So the component that combines the translation and rotation is 0. The last one is mass moment of inertia, which I recommend you to look at from the pre-calculated tables. There's plenty of those available for different shape of the bodies. Or if you want to make your life difficult, you can use a volume integrals, like it is the case here. So I'm integrating from x direction from L minus L divided by 2 minus L divided by 2 to L divided by 2 minus h divided by 2 to h divided by 2. When I do that, that's going to be my mass moment of inertia. Okay. Now, That's going to be my mass matrix. So this was a 2 by 2 matrix, the one you can see here. This was the vector that turned out to be zero vector. And this is my mass moment of inertia, which is a scalar component. Yes. So this entire, so your question is like this entire matrix? No, this entire matrix consists of one, two, three rows, and it's one, two, three columns. This column is associated to r x dot dot, r y dot dot, theta dot dot, as is this one too. Okay, makes sense. Makes sense. Okay, let's make another one. We're almost there. Last things to do. So this is we're almost there. After this, I only have one in-class quiz, and then you're off the hook. Good. You good? Okay. You good? We all good?
Yeah.
Are we all feeling strong?
Yeah.
Very good. Very good. Okay. The next one, same, but with the minor difference. No, major difference. Major difference because look at where my body reference coordinate system is located now. It's in one corner of the box-like body. So it's here. This is my body reference coordinate system. How this is going to affect my life? Of course, it's going to affect my life because my integral boundaries will be different. Because now I'm getting started here and I'm ending here. So obviously my x direction, my boundaries are from 0 to L, and this direction is from 0 to H. So that's a major difference. And again, oh, this is obviously a typing mistake. That should be H. Oh, then this is a very messy. I need to correct this before I place this in Moodle side because this supposed to be, it's like this. That is correct. Okay, anyways, you're going to get the mass. Yeah, this is correct. And then this is supposed to be, of course, H. This shouldn't be W, but H. From 0 to H, and then the W should be here instead of H. That's the two typing mistakes. But now when you look at the final outcome, so that 2 is a 2 by 2 matrix. And take a look at how much that is affecting the mass. No effect to mass. Of course, no effect to mass because, if my body weight would change depending where the coordinate system, that would be a fantastic weight loss technique, and I would be a millionaire because of that. But that's not according to physics. That is not changing with respect to where the body reference coordinate system located at. So it would mean that if I would hang myself here, or in my neck, or in my toes, my body weight is all the time same, which is all the time same. It's not depending where I'm hanging. Okay? But it will affect the other components. All right, here's a component that is combining the translation and rotation. This is going to be very, very messy. And now my integrals are such that it's going to be 0 to L, 0 to H. Again, I'm not going to take a look at the details, but this is what I'm going to get as a final solution. Here too, the parenthesis seems to be somehow a little bit off. And my last component, which is a mass moment of inertia, I'm going to again use my integral boundaries as it is set here. And look what it is this time. So it's going to be mass divided by 3, whereas earlier it was mass divided by 12. So obviously, resistance in this case is higher because the mass is divided by 3 only, not by 12, which makes sense. Because try to move the pen from here, comparing to here, here is easier than here. Okay, makes sense. My last in-class quiz. Oh, not yet here. So this is, I'm combining the material. So this is my 2 by 2 matrix. This is my vector. And this is my mass moment of inertia. Okay, how much the body mass? Read this carefully. How much the body mass increase, decrease from these different cases? Body mass. Body mass. Okay, how much I'm gonna weight if you're gonna lift me here, or if you're gonna lift me here in my neck, or if you're gonna lift me from my toes, from my shoes. What's gonna be my body weight in this case? Well, just a second. Just a second. Oh, hold on, hold on. So it's okay. So you see it already. Okay, so how much the body mass? Okay, you don't see this. How much the body mass? Let me repeat. Mass. Mass. Changes depending where you measure it. And there are two cases which is not shown here, but they are shown here. So if I put if I, it will be easy to say if I lift my box here, or if I lift my box here, how much is weight? How much it changes? Now the options are decreased by L divided by 12, no change. Increase L divided by 12, increase L divided by 3. Success rate
99.
99,
Yeah.
99, 99. Okay, that's should be
99.
okay. So 99.
Let's increase
Oh, he
the
becomes
range
to
of
be okay. So you
it's
want
from
to
the range of from 90 to 100. I get a coffee, and if it's below, you get a coffee. How about that?
I'm gonna give you a coffee anyway, so I want to offer you a
Yeah.
coffee anyways. So, but interesting to see this. This is interesting to see because you know what can happen easily when you get involved with the math is that you get confused about reality. That happens so easily. You know, remember when I claimed that we all here because of the redundant constraint that we are locked, the door is not able to operate because I proved that this is not able to operate. That happens so easily. And here, this can happen too, but we'll see. Okay, so let me take a look how many, because we are supposed to close this time. So we have, okay, so we're good. Is it going to be 100% or not? 100%. You're saying 100%. So I'm saying 70%. 70%. Oh, my, so close. So close. Almost. Almost. But it happens so easily, you get confused. Because the math make your brains to somehow get distracted.
Yeah.
Okay, guys. So all downhill. So we're gonna keep on going down. Next week is gonna be. Remember, I promised that there's gonna be these big days in your life. Learning how to run the kinematic analysis, but that's nothing comparing running dynamic analysis, and that's gonna be next week. You're never gonna forget that. So it's gonna be what day is that? 10th of October. So there's a life before and after. Big difference. Yeah, so it's almost like you don't believe me.
No, we do believe you.
Okay.
We've been there.
Okay. All right, guys. So I'm gonna close the streaming here. and see you guys on Tuesday.
Sure.
Same time, same place. I was missing you a little bit.
Okay. Or missing
Okay.
the coffee.
Yeah, coffee.